Welcome back to Zenith Poker. Today we'll be continuing with our Foundations series, and today we're looking at equity. So equity is a very important concept to understand in poker, but in order to get to equity, we need to first understand some other concepts first. One of them being expectation or expected value, right? So let's start off with a definition. So the definition of expectation or expected value. Okay. So the definition of the expectation, right? This particular definition is probably going to be new to a lot of people, but this definition is actually one that we're talking about in probability theory, right? So if we have a random variable x, and let's say that we have a function of that random variable, f of x, which takes in inputs from the domain omega and then outputs a number, any kind of number, right? So any kind of real number, right? And we also have a probability mass function, right? Subscript x, so this probability mass function is related to that random variable of x. Then the expected value, okay, the expected value, capital E, because it's a special type of function. The expected value of that particular function, f, of the random variable is equal to the sum over all possible x combinations, all possible versions of x, f of x, so that function, times the probability mass function, p subscript x of x. Okay, so if you're asking me, like, why do I need to know this? This definition of the expected value, the expectation, will be useful in loads of applications, all right? So we have the expected value of some function of the random variable. It's equal to the sum of all possible versions of x times of that function times the probability mass function of that particular x value. Okay, so that's the first definition that we want to look at. And now the next definition. So let's have a look. So I've got another definition for you. All right. This one's going to be a little bit more poker specific. Now I'm going to call this function, it's a special function. We're going to call it the showdown function. All right. So the showdown function. This showdown function is a poker specific function, and that we can say for player I, right? So for the ith player, I, right? The showdown function for that player, let's call it theta sub I, and this is going to have some inputs, right? It's going to have some inputs. Those inputs are going to be B, which is the final board, and let's say H, right? h. This h is actually a vector. So let's call it that. It's a vector in the sense that it's actually just a list of possible hand types, right? So it's going to be h1 ... hm. Okay, it's a vector that just represents all of the hands of all the players, right? So this is the hands of all the players, of all players. Right? So it's the hands of all the players, or it's all the players that have reached showdown, or if they haven't reached showdown, it's just a zero, right? So it doesn't matter. Okay. Then the showdown function itself, theta I. All right, so theta I is the showdown function for player I, and it takes as input B, the final board, and this H vector, so all the hands of all the players, whether they're involved or not involved. Right, if they're not involved, then it's just a zero. And this function spits out a number. Right, you can spit out the number 1 if player I wins, 1 over n if player I chops with n players. Right, oops. Running out of space here. Let's move this over. If player I chops, and 0 if player I loses. Okay, and this is at showdown specifically. Okay, now this showdown function, it basically, all it does is it takes the final board and the hands of all the players, and it tells you whether or not player I wins, loses, or chops the pot. Okay, and that's with all players, whether they've reached showdown, not reached showdown, doesn't matter. Okay, if they haven't reached showdown, then their hand is a zero, right? So it just doesn't really apply. Okay. All right, we have enough space. Let's move over here. Let's go up. Okay. All right. Now that we've got these two definitions out of the way, we've got the definition for expectation and we've got a definition for showdown about a showdown function. We're going to combine the two together. Okay. We're going to combine those two together to get equity. Okay, so a definition. So definition of equity. All right. And now let's take our equity and we are going to call this equity for player I. We're going to call the equity function Q sub I. Okay, so this is the equity function. All right. Now, the equity function is going to take in some values. All right. It's going to take in some values. It's going to take in B. It's going to take in B, which is the current board. And it's going to take a random vector. Okay. And stay with me here because I'll explain what this means. A random vector. Let's call it X. And this random vector is a list of random variables x1 through xm. It's a list of random variables representing the hands of all players, right? Or 0 if they're folded, okay? So this is a random vector that just represents the hands of all players. So just as in the previous sort of video, you can represent an unknown hand as a random variable. We have a random vector, which represents, which is a list of random variables, which represents the hands of all the players. So, and then another thing that we have to define, we have to talk about is this particular number, this particular set. So I have a set R sub B, okay? R sub B. What's going on here? R sub B. R sub B is the set of all possible final boards. So it's a set of all final boards following from B, okay? So say you've got a flop, right? That flop is B. R sub B is the set of all the final boards that you could possibly make with B as the flop, right? As an example. And now from R sub B, I'm going to define another random variable Z on R sub B with a probability distribution related to the set of all final boards. So it's uniform random. Okay. So it's all possible final boards related to B. Okay. And that's uniform random given that you don't really know anyone's hand. Okay. So say you've got a flop and Z is the random variable that actually represents all possible final boards. So you don't know what the final board will be. Z is in fact the random variable that represents the actual final board. You don't know what it will be because you can't see the other two cards that haven't been dealt out yet. All right, so let's put all this together. Our equity function, Q sub I, and remember it takes as input the board B and the random vector X, okay? And associated with that random vector is the distributions of all the players. This is defined as, right? So we're defining it as the expectation or the expected value of the showdown function for player I with the with the random variables Z, right, which are related to all the final boards, and the random vector X. Okay, so this is our equity function. Okay, it's defined as the expectation of this particular function, and it's got some random variables here, right? So it's got a random vector Z comma X. All right, and to explain that a bit further, this particular function, this expected value is in fact equal to, if we put all of the previous information in, we put the showdown function in to the expected the expectation function. We combine those two together, and we see that we get a sum. Okay, we get a sum of all Z's in the set of all possible runouts coming from B of X vector in the set of all starting hands for M players for the showdown function, here in this case for player I, for Z, comma, XP. Now this is a joint probability mass function, Z, comma, X, taking in those particular inputs, Z and X vector. Okay. And that seems like a lot, but basically all this is saying is that the equity of player I, the equity of their range, right, of their distribution, is how often that hand wins at showdown against all the other players, right? It's the average of how often that hand wins at showdown against all the other players given that board, right? Given that particular board B, right? And all possible runouts from B, right? Assuming that the runouts are uniform random, which in our modeling of the deck, they will be. Okay. This vector here, right? This vector in this particular set is just the set of all hands for all players, right? It's the distribution of all the players' hands, including player I, right? So it's how often player I wins at showdown against all the other players, given this board and all of its possible runouts. Right, this PZX number here is the probability mass function, right, for that particular runout given the set of hands, right? Okay, so that's probably quite a lot to chew on, but we will go through one example quickly just so that we can understand what I'm talking about here. All right, so one specific example. Let's say we're hero. Got hero. Should be an E, hero. Hero's hand is the Queen of Spades, Ten of Spades. All right. And then villain's hand is Ace of Clubs, Ace of Diamonds. And then we've got the board. All right. So the board here is, let's change the color so we get some differentiation between the two. So the board is the Nine of Spades, Six of Spades, Two of Diamonds, Four of Hearts. Okay, so we're on the turn at this stage. Now, we can see that hero can only win at showdown against villain's aces if hero draws to the fifth spade, right? Makes the flush. Okay, so hero's got four spades, and hero needs the fifth spade. Okay, so let's do some definitions. So let's define x1, right? The random variable as hero's hand, right? And this is x2, right? Villain's hand. We've got the board, B. Now we need to find, in order to figure out the equity, we need to find all possible runouts, right? All possible runouts. So it's going to be the list of all possible runouts. I'm not going to list them all here, but it's basically this board plus every possible river card, right? Because given that we know these two hands, right? It's every possible river card. Okay. So sub B is going to be the set of B, which is this board, plus every possible river. Okay. So if we put all that together, right, how many rivers will improve Hero's hand? So how big is RB? There's actually 44 different river cards. Right, so there's 44 different runouts. And only 9 of these runouts, right, will have a spade. 9 runouts have a spade. Okay. So then if we put all this information into our expected value function, right, we see that we end up getting an equity of 9 divided by 44. And the reason why that's the case is because this showdown function, the showdown function for hero is going to be a 1, right? It's going to be a 1 when the spade comes, and it's going to be a 0 when the spade doesn't come. Right, when there's no spade on the river. There's no chopping, so I don't have to worry about that. Okay. So then expected value essentially simplifies to how often we expect a spade to come on the river. Right? Pretty easy, right? So then equity. So here is equity, Q1, given our run out B, right? With the 2 spades. And we've got hero's hand, right? Actually, let's write it out in full just so that you can see what's actually going on. We've got the board, all right? The board is the 9 of spades, 6 of spades, 2 of diamonds, 4 of hearts, okay? We've got hero's hand, which is the queen of spades, 10 of spades, and then we've got villain's hand, which is the ace of clubs, ace of diamonds, all right? This equity, the function, the output for this is going to be essentially the expected value of the showdown function. And because the showdown function is just a 1 or a 0, right, we end up getting the expectation of the showdown function given the board B and the random variable Z. Right, sorry. The random variable Z should be here. Given R, queen of spades, 10 of spades, and ace of clubs, ace of diamonds. Right. Okay, so it's the expected value of the showdown function of Z, which is the list of all, is the random variable representing all possible coming from this board. And then we've got 2 hands. Okay. And then the expected value of that showdown function is just the sum of all possible Z in the runouts of the showdown function for player I of Z given the hands, right? Given the 2 hands. And then hero and the villain's hand, right? This is just going to be a list of 1s and 0s all multiplied by 1 over 44, right? And it's going to be 9 1s and 35 0s, right? So then basically that's just going to lead us to the number 9 over 44 as our equity. So the equity of hero is 9 over 44, which is about approximately equal to 20.45%. All right. So that's just one example. But this way of calculating the equity using this this formula here, this definition here, will work for any number of players and any board at any stage in the game. All right, which is why this is so powerful. So I've shown you one example of that with just two hands on the turn, but it doesn't necessarily have to be a specific hand. It could be a range of hands with a distribution for either player. It could be 3 players, 4 players, 5 players, any number of players, any number of hands in the distributions for each player. And that gives you the equity for the player I. Okay. So just as a recap, we first looked at the expectation, right, or the expected value, how we define that. The expected value, how we define that. Right, the expected value of a particular function is just that function times the probability mass function, and then we add up all possible ways we can do that. And then we define the showdown function, which just gives us a 1, a 0, or a fraction of the pot, depending on whether we win, we chop the pot, or we lose. And then we take our equity, the equity, and we combine those two previous terms together. Our equity is the expected value of the showdown function. Okay, it takes it for any number of players and any board at any stage. So their board could be 0, say for example preflop. All right. So I hope you learned something. Let's call it the end of this video. It's been a little bit long, and there's quite a lot to chew on. But I will see you all in the next one.